Algebraic calculus, we got unit 3, lesson 3, our last lesson of working with exponential growth and decay before we jump into logarithms. And yeah, we've got, from the notes, similar to the notes that we had the day before, we've got this principle with a rate divided by n. Okay, so P of 0 being the initial interest, and then P of t is the output, the principal that you get at any given time. And this is for compound interest. But as you compound it, and you're compounding it to smaller and smaller, or more and more amounts of time in a year or whatever, then you switch over to the continuously compounding equation. So we already had the notes on this on the previous day, but let's go ahead and apply this. So let's make our answer key. All right, if we have $500, there we go. There's a starting amount, so 500. No matter what, I'm going to be starting off with that. Is in an account earning 1.2% interest. That's not a lot. That's 0.012 as a percent. As a decimal. Compounded annually. Now, right there, they said compounded. I like that I have these notes here. Compounded, not continuously compounded, but it's compounded, and then they use the word annually. Every year. How much money will be there after 3 years? This is just using that formula. So since t, the amount of time, the years, is not getting broken up into any number of years, we can just use 500 times 1.012, adding that amount on to 100%, not dividing that rate into any amount. So it's just that, those two added together, and then time is 3. Honestly, this is just calculator work. And typing this in the calculator the correct way. So we're going to have 500. That's not getting raised to a power, but the part that is getting raised to the power is the 1.012. That's getting raised to the power of 3. And yeah, so we got 500. Oh man, we left that in the account. It's earning 1.2% interest. And after 3 years, our account now has $518.21. It earned $18.21 in 3 years' time. That is crazy. It's like nearly nothing. Okay, let's move on. Write an expression that gives you the amount of money in an account earning 2% interest compounded weekly, 52 weeks in a year. That number after t years if p dollars are invested. So we got p dollars are getting invested times 1 plus 0.02 divided by 52 times 52t. And that's why, like a lot of times in the expression, you'll see the n written in front of the t, is because we tend to write this monomial, not T52, but 52T. We tend to write it in that order. There we go, done. Number 3, the table gives, so we could put an A in front of that too. The table below gives the amount of money in an account that compounds interest annually, so every year. Time is given in years, T is equal to 0. Represents the day the account was opened. There we go. What is the annual interest rate? So our form, this is just asking for the interest rate. So let's look at what's happening each year. Just take one value and take it and divide it by the year before. So 365.0 and 50 cents divided by that amount. So it's 1.043, which means 4.3% is getting added on. That we should get that same decimal if we take any two of these and divide it by the one before it. So 41.95 divided by 3971.19. Boom. The same decimal? Yes. All right. Now, little rounding error here. Why isn't it the same exact number as what we got before? That's because there's pennies here. There should be a certain amount, a fractional amount of a penny. But yeah, we're not even minting pennies anymore, so let's not even bother with that. Number 4, Romania is opening. Romania? Okay, that's a name, not Romania, but Romania is opening a savings account. She has the option of earning 4% interest once a year, 2% twice a year, 1% every quarter. There we go. Which option should she choose? She wants to maximize her amount. So here's the thing. If we take 4%, okay, and we add one whole plus that 4%, we get 1.04. That's the annual interest. All right, but if we take that 2%, 2% interest twice a year, so let's see, how are we comparing this? Yeah, let's see, I'm looking at that. So that's 2% that gets used twice a year. Okay, so that's not an annual interest. If we wanted to find the annual interest, we'd be adding that on, but we'd be raising it to the power of t. All right, t, but this is twice a year, twice. Okay, so this is the amount that gets used every t years. All right, this 2, I can multiply that. I can give that power to the 1.02 to the power of 2, and now it's expressed like this. So this is the percent each half of the year. But if I raise it to the power of 2, 1.02 raised to the power of 2, I get that. So 1.0404 is the annual, so 4.04% is the annual rate, okay? So this one is slightly better. Now let's do the 1%. So 1 whole plus 0.01, but let's raise that to the power, that amount of 1.01, okay, is getting used every quarter, 4 times a year, 4 times a year. So I could take that 4, bring it in, and this gets raised to the power of 4. And on the outside, we just keep that power there. All right, so it's the same as doing this to the 4th power plus this part to the 4th power. It's mathematically the same thing. We can add these together because 1 to the 4th power is just 1, so it's going to be 1 plus whatever this is to the 4th. Anyway, let's go with that. Okay, 1.01 to the power of 4, and we get that one's slightly better. We get 1.0406. All right. So this is like 4.06%. Here's the thing. This is like super picky. Doesn't really matter in the whole scheme of real life. All right. This is a savings account. You're not putting money in a savings account to really earn money. You're just putting it in for stability. All right. But in general, this one would be the better account. Slightly pays a little more. Any normal. The vast majority of people are only putting, maybe a few thousands of dollars in this, not hundreds of thousands, not millions of dollars. If you had millions of dollars, this definitely matters. Maybe hundreds of thousands of dollars, this matters. But a normal person with a normal savings account, this isn't going to matter that much. Anyway, let's move on. That's my little rant. $10,000 are put into an account earning 3% interest. How much greater is the amount in the account after 5 years? 3% interest if it's compounded continuously, compared to if it's compounded monthly. So we're going to do 2 different workups for this. We're going to take this $10,000, all right, and we're going to be doing it compounded monthly, so that's going to be 1 plus the 0.03 divided by 12 months raised to the power for 5 years to 12 times 5. So there's 12 times 5. There's 60 of these periods, and so that gets applied 60 times versus continuously. Remember, our continuous formula has that principal times e to the power of the rate. Okay, let's just go ahead and find that one and talk through it. It's the first time we got this one. Okay, so we got our principal, our e, the number e, and the rate times the time. So we got 5 years. 5 years is what we got, and our rate of 0.03 times 5. That is our power times. Okay, calculator work. All right, so we got to make sure we have order of operations. We're going to have $10,000 times this whole thing, 1 plus, in parentheses, 0.03. 0.03 gets divided by 12. Close the parentheses twice to lock all that in. Raise it to the power of parentheses 12 times 5. I already know that's 60, but I'm just going to put the whole thing in. And $10,000 turns into $11,616. All right, $11,616.17. I'm going to round that up to that penny. That is what we're going to take away from the amount that's going to be bigger. All right, so we still start off with $10,000, and we're going to be multiplying that times E. So I need second E. E to the power of 0.03 times 5. All right, boom. That's a lot shorter, and we get 11,000. $11,618.34. Oh, wow, what a big difference. In the whole scheme of $11,000, this is nothing to have a $2 difference. My God. All right, anyway, let's subtract from this $11,616.17. These money problems really tick me off because, like, I feel like I'm a real human being who's like, I don't have $11,000 to put into an account and everything, and like, I'm gonna care about $2. You know who cares about these amounts of money? These are gonna be big banks where they have thousands of people investing thousands of dollars, and these dollars over a couple dollars over hundreds of thousands of customers. That's gonna matter. So $2.17 is our answer for this. That is the difference. And who cares about $2.17? Well, it's the predatory people setting up banking accounts and stuff like that, who credit card accounts. $2.17 extra on, again, thousands of customers' bills means more income for those people who are giving out those loans. Frustrated. All right, anyway, let's move on. Number 6. I gotta go soon, so like I'm not sure how many of these we're gonna get through, but anyway, money is invested into an account earning 8% interest. Okay, if the interest is compounded quarterly 4 times, okay, how many interest payments are earned over 5 years? Well, that's relatively easy. So it's 4 times 5 years. Interest is being added on 4 times 5. That's 20 times. All right, so that's relatively easy. If the interest is compounded quarterly, by what factor does the amount in the account grow each time in interest payment? So that's taking the 1 plus the 0.08 getting divided up into 4 parts. Every time they compound the interest, that's the amount. And so what is that? It's less than 8% because you're taking that 0.08, you're dividing it by 4, which is 0.02, and you're adding a 1 on it, so it's 1.02. So instead of 8%, that means that it's 2% is getting, so let's see, what's the question? By what factor? So our answer is this. That is the factor. If they said by what percent is it growing each time, it's 2% growth, but that's the factor. That's the number we want. If interest is compounded monthly, okay, there's 12. How many interest? 5 times 12, so that's going to be 60, okay, 60 of those, and 1 plus 0.08, yep, divided by 12, same thing. Well, 0.08 divided by 12 is going to be pretty small. 0.08 divided by 12, and then we get that answer, and we add a 1 to it, and it's going to be, 1. All right, 1.006 with a repeating over the 6 is our answer for that. That's, yep. So 0.6 repeating percent, or 2/3 of a percent. 2/3 of a percent. 1% would be that, but it's 2/3 of a percent that's getting added on. Okay, so, or it's 100 and 2/3%. That's what that's equal to. That's, okay. If $850 is placed in an account earning 1.7% interest is compounded continuously, how much will be in the interest? All right, 10 years. So we are using our 850 e to the power of 0.017 times 10. 10, oh my God, times 10. So this would be 0.17 is our power when we multiply it by 10. Okay, so yeah, 850 e, and raised to the power of 0.17. So we will have $850 after 10 years at that rate turns into $1,007.51. Put a dollar sign in front of stuff, will you? Okay, number 8, which of the following scenarios would best be modeled by continuous exponential growth? Okay, so think of stuff that doesn't happen one at a time, but is constantly happening, infinitely small amounts of time. Number of rabbits? No. Rabbits reproduce in chunks of time, generations. Number of people who hear a rumor at school. No, that rumor is going to spread by individual people, not infinitely small amounts. The temperature of a mug as it cools. Absolutely. As the temperature is going down, we can take and reduce the amount of time infinitely small to calculate that. The height of the basketball after each bounce. Yes. All right. As that bounce is continuously, yeah. Oh, well, let's think about that one. No, the height after each bounce. This isn't it. It's height. This is after each bounce. So we're going to have a bounce, then a bounce, then a bounce, then a bounce. And we don't care about the heights in between. That is a no. The only answer is C. That one. 9. $900 are placed into the account, earning 3% annual interest compounded continuously. A bank wants to offer an alternate investment option that accrues interest only once a year. What is the smallest interest rate that they would have to offer so that the second option is more lucrative than the continuously compounded? Okay, so if we did so for each year, so let's say our time here was 1 year. So we have 0.03 times 1 year, e to that power. All right, let's not even worry about the $900, but e to the power of 0.03. That's for 1 year. 1 year. This is equivalent to an annual interest rate of 1.03. Okay, which is 3. Let's see. 0.045. So if I move the decimal place over, so 3.045% in 1 year is what this is mathematically equivalent to. Will 3% do it? No, too small. This one looks like it would do it. Not that one. That's too much. That's too much. It is B. Great. Man, it's nice when the answer works out to be the same thing as the answer key. Let's move on. Suppose that a savings account earns interest at 100% annual interest. What? Explain why it is possible for the account to have more than double its initial value by the end of the year. I'm going to refer to this. Go ahead. Answer key's right here. It's because it's continuous. It's because it's going to be, continuous annual interest rate, but it's possible for that 100% to be applied continuously. And if we did e to the power of 1, all right, let's look at that. E to the power of 1 gives us 2.7. Yeah, so our annual interest rate is 2.71. If we take away 1 whole off of that, that's equal to 171% growth annually each year. Let's move. Yeah, that's it. Take care, folks. Bye.